Okay, so we'll continue on from chapter 3, okay, 3.5, factors that can affect the performance of a CPU. All right, so when we talk about CPU, we're talking about the central processing unit. And in this part of the chapter, we refer to how quickly the CPU can process an instruction, okay? So the three main factors we talk about when we're talking about performance of a processor, essentially, that's the CPU. This is the number of cores it contains, all right? The clock speed and the cache size. All right. So each CPU can have more than one core. Either you can have one core, 2 cores, 4 cores, 6 cores, 8 cores, and so on. The more cores you have, the more instructions you can then process, right? So for some CPUs, for example, have 4 cores, right? This is often called a quad-core processor. You might have seen dual-core processors, that's 2 cores, and the quad-core processors, that's 4. And that they can perform 4 fetch, decode, execute cycles, so FDEs, okay, cycles, all at the same time. All right. So each one can do a process all at the same time, right, running parallelly, meaning they're running at the same period. So you could have one core, another core, another core, another core, and then it all run a separate process at the same time, which you can't do on a single core. All right, you have to have something called a thread or a virtual core that would have to run separately, which is very difficult to have. Sometimes you will have threads, so that splits the core into 2, but in this case we're talking about just a single physical core, meaning that your whole CPU is split up into 4, all right, and each one would be a single core running separate processes parallelly, all right, parallelly meaning at the same time. Okay, then we talk about clock speed. So clock speed is the frequency that our CPU can run at. So when we talk about clock speed, we talk about the internal clock speed. All right. So this speed is measured in hertz, hence frequency. Okay. It's measured in hertz. You might have seen it as just Hz. All right. So a CPU that has a clock speed of 1 hertz is able to process 1 instruction per second. So that's 1 hertz. But generally speaking, nowadays we talk about gigahertz. So you can think a kilohertz, that'd be 1,000 megahertz, a million. So a gigahertz would be a billion, basically. So if you have a 2 gigahertz or 3 gigahertz processor, it can run 3 billion instructions per second. All right. So at one stage, the clock speed, we increased the clock speed of a CPU in order to speed up our processing power, right? But at some point, once we increased the clock speed too high, it started causing problems with heat dissipation. So we had heat problems. It would damage the computer, etc., or the processor itself. Generally speaking, we're now recently capped at about 4 to 4.5 gigahertz maximum on most processors. All right, but we have started increasing the number of cores. All right, in order to get higher performance. Then we can also talk about cache size. So cache size is basically the internal memory. All right, the internal storage size of the CPU. So the more internal memory we have, the more we can store, okay, quickly. So we're not talking about storing, for example, in the RAM. We're talking about just storing within the CPU, so that the number of instructions it can then store, all right, and then carry out all at the same time will be increased the more cache size we have. Okay, and remember, cache size speed is cache size storage is a lot faster, okay, than RAM, for example, or secondary storage, which we'll talk about later, such as your hard drive. Way faster, like way faster. So rather we'd have higher cache size in order to increase our speed, okay, especially when it comes to storage limitations. So next we're going to talk about input and output devices. So obviously you would know an input device would be, for example, a mouse, keyboard, touchscreen, etc. Okay, that's input. You're doing something and then it's sending that input to your device. All right. Then we can have an output such as a printer, your screen, that's an output, right? You do something and then it shows on the screen, that's your output. A projector is another example, all right? But sensors are also another type of input device in an automated control system. So a sensor can be a touch sensor, it can be a temperature sensor, it can be a humidity sensor, etc. It's for automatic systems, All right, so we can measure something, okay, whether we've touched touch sensor, or if the humidity is too high, temperature is too high, our automatic control system can then act. All right, and it would take constant inputs from these sensors. That would also be an input device example. Next, we'll go to data storage. Okay, so when we talk about data storage, we're talking about primary storage. Okay, previously we were talking about cache size, but that's the internal memory. So cache size would be above primary storage. It essentially is a primary storage, and it's part of your CPU. Okay, so that would be cache size. But then the next memory we'd have, because cache size is so small, we're talking about not even a megabyte of cache size. All right, in some cases. So with such a small amount of cache size, we're going to need extra primary storage, known as RAM and ROM. Okay, RAM you'll know from your PC. The more RAM you have, generally speaking, the faster your PC will get. So that's called random access memory. Okay, so it can be randomly accessed and written to and read from. So it can constantly put stuff into storage and take stuff out of that storage all the time. So that's called volatile memory. Volatile meaning you can change it anytime. All right. ROM, all right, is read-only memory. Things like your BIOS, for example, are generally speaking ROM. Okay, your BIOS can technically be rewritten since it's usually electrically able to be rewritten. Okay, I'm not going to go over exactly how that works, but for the most part, even if you switch off your PC, or even if it was short-circuited, for the most part, depending on where it was, the memory within your BIOS, for example, the BIOS is what starts up your PC on your motherboard, would not be erased. Okay, so it can't be erased for the most part. That means it's non-volatile. Non-volatile means it doesn't change. So whatever you put into that memory the first time around can't be changed. You guys remember DVDs? You guys know DVDs? Certain DVDs are rewritable, certain DVDs are not. The ones that aren't rewritable, you'd write onto the DVD once. Okay, maybe you put some music on there, whatever the case is, and then that DVD can then no longer be written on. Okay, you'd only be able to listen to that music, and then you have to get a new disc. It wasn't rewritable. Okay, that would be an example of that's similar to read-only memory. The read-only memory is something you only want to put in once, and you don't want it to be rewritten. You don't want it to be. It's very important. You want to keep it. All right, not to be stored in and taken out of. Not to be written and rewritten over and over again. Okay, so random access memory can be. That would be for your files, etc., that are being used at your PC at any time. That would be an example of primary storage. That's the first storage that we'd use. Once our RAM, okay, is full, okay, so we can't use any more RAM, we'll start storing stuff in our hard drive, for example. That's magnetic storage. So we use magnetic disks, basically, to store all of our memory. So for example, your 1 terabyte hard drive, we call an HDD, would be magnetic storage. We could also have optical storage, such as a DVD or CD or Blu-ray. Okay, it's optical, meaning we're using laser light. All right, so we're using laser light, magnetic storage, you're using magnets. Solid state storage, all right, that's another secondary storage. That could be like USB storage or SSDs. If you guys know solid state drives, it uses the same type of idea as USB storage, okay, like a USB or memory card, etc. Okay, so these solid state storages use semiconductor chips we call transistors. All right, transistors, basically a single transistor can switch between a 0 and a 1. You guys know binary. So each 0 and 1 has a single transistor. So transistors are actually very small for the most part. Okay, you can have larger transistors, but for the most part they're very small. And so you have literally billions of these at any time within your solid state storages. Okay, so that you can have enough space. All right, so for example, if you think about a 1 gigabyte USB, okay, that's very small. But a 1 gigabyte USB, think about it, has 1 billion bytes, and there's 8, right? 8 bits in a byte. So that'd be 8 billion bits, okay? And if each small transistor, okay, has a 0 or 1 in it, that would basically represent 1 bit. So you'd need basically 8 billion transistors in that single one, well, minimum, just to have that single 1 gigabyte. All right, so that's just an example of how small they are if you look at your USB. Okay, And USB is actually not a storage. USB is actually the connector. So when you see the connector of a USB, that's what we're talking about. Universal Serial Bus. Okay. When I'm talking about USB storage, I'm talking about just the storage part, so the memory card part. All right. When we say USB, we don't mean storage. USB means the actual connector itself. All right. Okay, so these transistors we're talking about contain cells. All right. We call them cells, or generally speaking, just transistors. Okay. All in a grid, so they're all together, right? And are wired together in NOR flash structures or NAND flash structures. So for the guys who've done logic gates before, you would know what a NOR gate and a NAND gate is. Okay, it's basically just an OR gate with a NOT gate at the end of it. So an OR gate would look something like this, and then you'd have a NOT gate at the end of it. All right. Generally speaking, we would just draw it like that. That would be a NOR gate. An NAND gate, we draw on the straight line and a NOT at the end. All right. Later on, I'll explain exactly how those gates work for those who haven't done NOR NAND gates yet. But basically, we use those gates either if we wire them together in a NOR flash structure, so that'd be parallel. Right, so they're parallel to each other, meaning it can be either or, okay, connection, or we use NAND flash structure. This is generally what we use, NAND flash. You guys might have heard of NAND flash before. NAND flash structure is in series, so we have multiple transistors in series with each other essentially. Okay, so parallel means, for example, if I had a connection, parallel would be several connections going next to each other. So if I had one single connection, it would split up to 3 different connections, all right, and continue. They're all parallel to each other. Okay, series connection would be I have one transistor, the next one's connected, the next one's connected, all right, like a string of light bulbs. All right, so each transistor is like that. But if one doesn't work, all right, gets cut out, then the rest won't be connected. Okay, but there's ways we can go about that, okay, getting over that. But for the most part, that's how a NAND flash structure would work. At first, all transistors are set up, okay, to be a 1 when you first buy your solid state drive, okay, or your USB storage drive. Okay, they each have a control gate transistor, all right, and a floating gate transistor. Okay, so when electric current reaches the control gate, right, originally the floating gate would be at 1, sorry, would be at 1. And then when electric current reaches the control gate that's sitting on top of the floating gate, all right, so we might have a floating gate and a control gate on top, something like that. All right. Once the current reaches the control gate can decide whether it wants to store it in the floating gate. If it does store it in the floating gate, that transistor is then set to 0. Okay, that means it's stored. Okay, not stored is 1, stored is 0. All right, stored in the floating gate, and the control gate controls whether or not it's stored. All right. So we'll stop there for today, and then we'll continue on from virtual memory 3.8 next time. All right.